Hi everyone, today we're talking about how you can interpret the slope and y-intercept for linear models. As a reminder, you do not need to write down everything that we'll cover in this video, but be sure to jot down important information and at least one example of each type of problem that we'll cover. Also remember that you can pause to jot down important notes, rewind to view information again, and fast forward if you think you got it, but be careful and make sure you don't fast forward too much that you miss out on something important. So for today's lesson, you're going to be given either slope and y-intercept, or just one of those, and you're going to have to explain what it means in the problem. So to review, the slope tells you how much the x and y are changing. Okay, your two variables are changing. So that's from your rise over run formula. The y-intercept tells you the starting point. So that's going to be where it intersects with the y-axis. If you don't have this in your notes already, make sure you have it down and use it while you're working on the examples. All right, let's dive into our first example. For this example, we have someone named Adriana, and they are gathering data, or they gathered data on different schools' winning percentages and the average yearly salary of their head coaches. So trying to see if there's a relationship between the amount of times they win and how much the head coaches are paid in millions of dollars in the years 2000 to 2011. She then created the following scatter plot and regression line. So the regression line is just your trend line or your line of best fit. The fitted line, they are telling you, has a y-intercept of 39. So they want to know, what does it mean if the y-intercept is 39? What's the best interpretation? So go ahead and pause the video and see if you can figure out what that 39 means. All right, so let's take a look at each of our statements. And also remember that 39, if that's your y-intercept, that's your starting point. And in this case, it's your winning percentage. So I'm just writing all that information down, the winning percentage. Let's go through our statements. Does the 39 mean that the average winning percentage was 39%? Maybe. I mean, the line kind of goes through it's the trend, so what's happening over time, the pattern. So A could be it. B says on average each $1 million increase in salary was associated with a 39% increase in winning percentage. So when I see this $1 million increase in salary associated with the 39% increase in winning percentage, I'm notice that it's talking about the salary and the winning percentage together. That sounds to me like it's actually talking about slope, because it's talking about how the two different variables, the winning and then the salary increases, are related to each other. So that doesn't seem right. C, it says the model indicates that teams with coaches who had a salary of $0 million will average a winning percentage of 39%. Okay, that could be it, because it's talking about $0 million. So the starting is 0 for the salary, will average a winning percentage of 39%. That could be it. And then the last one says the average salary was $39 million. Well, the 39 is for the winning percentage, it's not for the salary. So this one's the wrong scale. It's using the x-axis to talk about the 39 when the 39 is on the y-axis and it's talking about the winning percentage. So we're really going between A and C. Are we saying that the average winning percentage for everybody was 39%, Or are we saying C, the model indicates that teams with coaches who have a beginning salary, so $0 million, it sounds weird, but this is the beginning, will average a winning percentage of 39%. Think to yourself, is that for everybody it's 39% or just for the beginning? You should have picked C because that 39 is only for the beginning. Once you get to like over here, the average win is 85%. So it's not for everybody. It's only for the beginning salary amount. So you got to really read through and see what they're saying, because sometimes two will sound very much alike. And other times they'll give you the wrong scale. Let's try another one. This one says, Baruti, a ranger in Kruger National Park in South Africa, collected data about the elephant population in the park. She compared the foot lengths of the elephants and their shoulder heights, both in centimeters, and created the following scatter plot and regression line. So they're comparing foot lengths of the elephants and their shoulder height. They're trying to see if there's a relationship there. The fitted line has a slope of 5.89. So we know now they're talking about slope. That's not the start now, that's the change. And that's going to tell you the relationship between the shoulder height and the foot length. So be careful with that. They want to know, what is the best interpretation of this slope? So go ahead and pause the video, see if you can try it on your own first. All right, so like we said, the 5.89 is the change. It's telling us the relationship between the foot length and the shoulder length. What I want to do first, before I even look at my different statements, is I want to see what that 5.89 actually means according to my graph. So slope is supposed to be rise over run. So we're basically saying at the end, after we divided, we got 5.89. Okay, so that means the 5.89, we're going to put it over 1. That's the rise, and then the run is 1. So our rise, you want to look up and down. Up and down tells us the shoulder length. So 5.89 is the 5.89 centimeters. That's the shoulder length. Okay, and then the 1 is the run, so that's the foot length. So that's centimeters, and that's the foot length. Okay, so very important that we have the rise and the run figured out. So this is telling us that for every 1 centimeter long for that elephant's foot, there's going to be an increase of 5.89 centimeters long in the shoulder. So every time you have 1 extra centimeter of the foot, there's going to be an extra 5.89 centimeters in the shoulder. Okay, so now, and we just got that from our rise, the words here, and the run, the words going this way. Now let's read. On average, each 1 centimeter increase in foot length, okay, good so far, 1 centimeter increase in foot length, was associated with a 5.89 centimeters increase in shoulder length. All right, that one looks like it's good, but let's read the other ones just in case. Part B says, on average, each 1 centimeter increase in shoulder length. Nope, it was 1 centimeter increase in foot length. Wrong, that one has it switched. C says, we could predict an elephant with a foot length of 0 centimeters to have a shoulder length of 5.89. 0 centimeters foot length. 0 centimeters foot length would be here. So they're trying to talk about, for C, they're trying to talk about y-intercept. So that's not good. That answer is for y-intercept. That's the start. Not good at all. Last one. We could predict an elephant with a foot length of 0 centimeters to have a shoulder. No, the 0 again is talking about the start. So we don't like that one either. Sometimes they'll try and mix up your y-intercept and your slope. And this one was mixing up the order of rise over run. This is run over rise. This one is correct. You should have gotten A. Okay. So again, for slope, you got to get the rise and the run correct. You can look on your scatter plot. Rise is the y-axis because it's going up and down. Run is the x-axis going left to right. And then anything talking about zeros is the starting point, so that's going to be your y-intercept. Let me know if you have any other questions as you work on these problems, and I'll see you in class.